Be ready to write on your paper. Let's talk about this right rectangular prism. So we've got a prism when there's not a picture. Uh-oh. I'm frozen. I got it. And this prism, in our situation, has a length of 5 and 3, and it has a side length that we don't know, so I'm going to call it S. Who can tell me how I can get the volume of this prism? Ivy, what are you thinking?
Well, I can do like 5 times 3.
Okay.
And then
And what would I do at that base to find the volume?
times S.
Yeah, I don't know the height, except that I'm going to call it S. So the volume of this prism will always be 15. The base is 15, right? Times the height, S. And what that means is the height S can be like anything. And this will work for any prism as a base of 5 and 3. Does everybody follow what this function is? Okay, and there's not a ton of room here. But I actually, not a thing you'd have to do, but I really like a table in this situation where my independent variable would be the side and the volume would be the dependent variable. All right, so what are some nice side lengths we could test out?
5.
5, okay, let's start with 0. But we could get to 5. I'm gonna do let's just do 1, 2, 3, and 4 for now. Those are some nice numbers. And so along the x-axis, I know I'm going to have a side length. What is the side length going to pump out of my function? I'm going to put in a side length. Then what's that going to tell me? The volume. And that would be my dependent variable. I'm not going to label my y-axis yet because I don't know what scale I'm going to need. But on my x-axis, I'm going to go 0, 1, 2, 3, 4, 5, 6, 7, 8. So these are all the different heights I'm going to test out. And so I'm going to start plugging in heights. Now I'm going to take my attention to the table. When I have a height of 0, or a side of 0, what's my volume? 0, because there's only a base. That's only 2 dimensions. There's no volume. But as soon as I make that side length a 1 in my prism, I've got 15 times 1, which is 15. If it has a height of 2, what's the volume? 30. If it has a height of 3, what's the volume? So my one thing you can say is my rate of change or slope is 15, right? So I'm going to start plotting these points. Now, I know I'm going to 60, so I might want to go to 120. I'm going to number it by tens. I'm not going to get to 120, but close. Do you see how I didn't decide what my y-axis needed to be until I knew some values that I want for volume? Because if you just started numbering by 1, you can't even graph the first point. So we need to scale our axis. You could have a different scale and still be all right here, by the way. You could go by 20s or something. So next I'm going to start plotting points. I got 0, 0, 1, 15, 2, 30, 3, 45, 4, 6. And I can keep this going all day. I'm just going to go 8. If I put in 8, I know I'm going to get 120. Oops. It'll be up here. Y'all, what do you notice about this function? It's linear. I also want you to take note that it is continuous. I didn't just use my reference points. Why would this be continuous? Why don't I just have the dots from my table? Why am I connecting them? Zeph?
Because it's marking like all the points in between. Like if the height was pi, like that's something on there.
Yeah, there's an infinite number of heights it could be, so I need to show my infinite answers, okay? It's not just whole number side lengths, right? So here's this. Now, the next thing I want to ask you is what happens when I double the side length? So what points do you guys want to reference to check the doubling? So we're looking at side length. We can't double 0 because it's just 0. What number do you want to start with, and what do you want to... Let's start with 1. Okay, so 1 was 15, right? So if we double the side length from 1 to 2, how would you explain how the volume changed? It doubled. So let's test triple. If I went from 1 to 3,
45.
what did 3 pump out? 45. If I triple, it tripled. So what would you guess? If you quadruple, what do you think it's going to do?
60.
It's going to quadruple. Interesting. Now, here's why. Let's say this block had 1 for the height. If I just make that height 2, how many directions is it changing in?
1.
Just one direction. It's the same base, it's just going up higher. So therefore, that's only going to change by whatever the factor you multiplied is. It seems as though that works, right? You can even do 4 with 60. What would 8 be? If you double it, 120. So if you change one dimension, that's all we changed, one dimension, one side, the volume changed, that's the same factor that you change the dimension, right? When you doubled, it doubled. When you tripled, it tripled. When you quadrupled, it quadrupled. Okay, stash that up in the brain noggin. So remember, sustained. This takes effort, but it's good effort. Let's keep sustained effort here. So, oh no, this isn't a cone. This is a cylinder. So I've got a cylinder right here. Okay, and it's got a radius of 5. The height, we don't know it. Who can help me out with the cylinder equation for volume? Meredith? Yeah, I take the circular base, multiply it up by the height, right? So from my picture, or my situation, what can I actually put into my function? Which value? I can put 5 in for what, Meredith? Radius. So I've got 25 pi times the height. Now if we did 25 pi, what is it, like 78 and a half?
Yeah.
I'm going to rewrite it as this. So here's what I want to make sure everybody understands. If I know my radius has to be 5, the only thing I don't know then is the height. But this volume equation that I have right here will tell me what the volume of all the cylinders are with a radius of 5. You follow? I just simplified everything else. So what you're going to do now, much like we just did with the prism, we're going to test it out. We're going to put in a height and pump out a volume. I want you to use these inputs into the function, 0, 2, 4, 6, 8. We don't have to do, we'll cut down some of the work volume. Again, this is going to take a little sustained effort because you need to decide on an X scale, a Y scale. What should you do first before you decide what the Y scale is, though? You need to know the independent and the dependent variable. You also need to know how high you would need to go, right? All right, let's get after it. Let's see this graph. I get this big idea. I double the height. It gets double the volume. I 1/8 the height. I get 1/8 the volume because we changed one dimension. You might be asking yourself, what happens if I change 2 dimensions? And I'm going to say, hold on to your seat because we're about to find out. Yeah, same thing, only different. So we're going to analyze what happens if we're going to start changing 2 dimensions instead of just 1. So we're going to look at a cone. Who can tell me volume of a cone? Sean? 1/3 of that cylinder we're rocking. And for our situation here, our cone has a height of 7 units. So where can I put 7 in my function? Radius or height? It's height, right? So everybody see, we know the height of this, and that's it. So we're going to look at every single cone that has a height of 7. So what's changing the dimensions of the cone then? If we know the height is always 7, the radius, so our base is going to be getting bigger or smaller, right? Okay, but let's simplify this. To simplify this, in my calculator, I'm going to do 7/3 times 3.14. Because I can multiply that by, I get 7.33. So just to make life easier, we're going to get 7.33 r squared. I just multiplied all the other numbers that I could multiply together. I just don't know the radius because that's what we're changing. We're going to see what changes as we change our radius, which means we're going to see what happens to our cone as we make our base bigger or smaller. Okay? So I'm going to set up a table. I think the table is a good vibe for this. I'm going to pump a radius in, get a volume out. And let's look at 0, 2, 4, 6, 7, 8. Who's got a guess? Like if we were to double the radius, what do you think is going to do to the volume? Double, okay. If we triple it, what do you think is going to happen? Triple it. Let's test it out. There's only one way to find out. Let's do this thing. So I'm going to throw a 0 in there.
0.
It's 0, okay. You need 3 dimensions to have volume. I throw a 2 in there. What operation do we have to do first? Exponent. So 2 squared is 4. And so 4 times 7.33. I got 29.32. All right. That's cool. So you guys were predicting double it, right? So the next one, if your prediction's right, should be close to what number? Like close to 6. So let's see what happens. Let's throw a 4 up in there. 4 squared is 16. 16 times 7.33 pumps out a 117.28. What the junk? That's not 60. Something's going on. All right. If we take this further, if we tripled the 2 to get to 6, it should be somewhere around 90. Let's see what happens. I throw a 6 up in there, square it. I get a 36 times that 7.33. So if our radius is, 263.88. That's nowhere near to tripling the volume from number 2. Something's going on, friends. Okay, let's test out 8 just to test out. Throw an 8 up there. 8 squared is 64 times that 7.33 that we got from our dedicated height. 469.12. Wow, you would think today would be times 4, so somewhere around 120, but that's not anywhere close to 120. In fact, what's happening to our gaps as we increase?
They increase.
The gaps are increasing. So do we have a standard rate of change here? No. There's a pattern, but is that rate staying the same? No, it's kind of getting intense. It's like more and more and more. Well, let's take a look at what this graph looks like. 1, 2, 3, 4, 5, 6, 7, 8. And then I need to go as high as like, what, 500? So 1, 2, 3, 4, 5, something like that. You guys vibing with that scale? I'm going to have radius on the bottom, volume on the side. All right, so we got 0, 0. So you're thinking like, yeah, okay. 2, somewhere close to 30. Oh, it looks like a line. I could make a proportional line there. And then all of a sudden, 4 is up at like 120. Like, what? 6 is up at like 260. They're like, come on now. 260. And 8's all the way up at 470. My goodness. And then you go to connect your dots and you're like, man, that is not a line. So it looks different, doesn't it? We all acknowledge this looks different than when we changed one dimension. Well, if we're changing the radius, how many dimensions is that base changing in? It's wider in 2 directions, right? That base. Also, do you notice that the radius is squared? That's interesting. So let's go and figure out if we can figure out like what the factor is that's happening here, right? Because before we could double it times 2, we could quadruple it times 4. Let's see if we can figure this out. So I'm going to look at 2 and 4. And for my radius, we doubled it. How could I figure out what I did to get from one to the other for my volume? What operation could I use? So for here to here, I doubled. How could I figure out what I had to multiply by to go from 29.32 to 117.28? How can I figure out what I multiplied by? Divide it, right? So 117.28 divided by 29.3, guess what that is, guys? Times 4. That's not doubling, that's quadrupling. Interesting. Let's test out another point. let's go 2 to 8 actually. So you would think 2 to 8, it's quadrupling the radius, right? Let's see what this does. 469.12 divided by 29.32. So I'm going to divide the volumes. I would have to multiply that volume by 16. So there is a relationship here by the factor at which we increase the base, the area of the base. Can anybody see that relationship? So I multiplied the radius by 2, but my volume increased by a factor of 4. I multiplied my radius by 4, but my volume increased by a rate of times 16. Do you guys want to check another point? Let's go 2 to 6. Whisper to a neighbor. What do you think is going to happen from 2 to 6? So that's times 3 as radius, right?
No, it's gonna be times 9.
It's times 9 for volume. So there's a relationship between our radius and our volume changes. What's the relationship, Ivy?
Well, the one on the left is the square root of the one on the right.
Yeah, it's squaring
Yeah.
the multiplier. So if we extend this, if I were to make a radius 5 times larger, what would happen to the volume? If my radius, so when my radius was 2 times larger, my volume was 4 times larger. When my radius was 3 times larger, my volume was 9 times larger. When my radius was 4 times larger, my volume was 16 times larger. So if I'm 5 times larger on radius, 25. If I was 10 times larger on radius, what happens to my volume? 100. So how could we write that as an algebraic expression of some sort? Like, what's a general rule I could make for this? Whatever this factor is, what's happening to it? It's getting squared. Whatever my factor is of base growth is squared. And here's why. You ready for why? Here's why. The reason is, how many dimensions is a base? 2 dimensions. So let's just take a 2 by 2 base. Okay? What's the area of this? 4. So if I triple both sides of my square, I would be 6 by 6. And we found out triples 9 times the area, right? Which was 9 times the volume too, but 36. It's because we're not just stretching it in one direction. We're stretching it in 2 directions by that factor. Right? So before, we had the same box and just made it taller. Now, we have the same box and we're making it wider and taller in 2 different dimensions. So it's a times 3 times 3, or a times 4 times 4, or whatever that change is on one side squared. That makes sense? We're not just changing one thing, we're changing 2 things. And that happens as squared. What do you think happens if you change all 3 dimensions by the same factor? Cubed. Yeah. So if you stretch in 1 dimension, that's your factor. That's the big takeaway for today. If you stretch 1 dimension, that's just your factor, right? So if your 1 dimension is 3 times bigger, your volume's 3 times bigger. But once we have 2 dimensions that we're stretching, like length and width, for example, if you go half as much, 1/2 squared, or 1/4, would be your volume change. Because it isn't linear. Remember our graph? It's not a linear change because we're changing 2 dimensions. If we make it 4 times bigger, that's a times 16 for volume. If we did the 2 dimensions 4 times bigger. Because we're rocking 2 dimensions. All right? See the difference between 1 and 2? 1 keeps its factor. 2 is that factor squared. For 1 dimension to 2 dimensions. All right? That's the big idea. That's all you need to know to do everything today.